Hello and welcome back. In this video, we're going to apply some of the concepts we've been learning in Chapter 13 to a problem from the back of your OpenStax textbook. So the problem I've chosen is 1333, and it reads as the following. A bicycle tire has a pressure of 7.00 times 10 to the fifth newtons per meter squared at a temperature of 18.0 degrees C and contains 2.00 liters of gas. What will be its pressure if you let out an amount of air that has a volume of 100 cubic centimeters at atmospheric pressure? Assume that the temperature and the volume of the tire remain constant. So, what I've done is summarize this information over here on the left-hand side of the board. The pressure of the tire before we release the air is 7.00 times 10 to the fifth newtons per meter squared. We're not told that that's gauge pressure, so we're going to assume that that is absolute pressure, which is the pressure that we need to apply the ideal gas law. We're also told that the temperature of the tire doesn't change. So I'm setting T1 equal to T2. The old temperature and the new temperature are the same. They're 18 degrees C, but we use units of Kelvin when we use the ideal gas law, so I'm immediately converting that to Kelvin. We're also told that the volume doesn't change. So V1 is equal to V2 is equal to 2 liters. A liter is not the standard unit for volume, so I've converted that to cubic meters, which is the standard unit for volume. We're also told the volume of gas that is released and the pressure that is released at. I've chosen to use the prime symbol to keep track of that volume and corresponding pressure. So V prime, the volume of gas released, is 100 cubic centimeters. Converting that to the standard unit of cubic meters gives us the volume released. And then P prime is the pressure that that volume is released at. That's atmospheric pressure, and I've given that as the 1.013 times 10 to the fifth newtons per meter squared. I've also identified what it is we seek, which is the new pressure P2. And I've also written down Boltzmann's constant here because it also appears in the ideal gas law. So here is the picture of our tire. Originally, it has some pressure P1, volume V1, temperature T1, and number of molecules N1. And then a volume V prime is released, and of course that corresponds to a number of molecules N prime. And when that number of molecules M prime is released, we now have the tire with some new pressure P2, volume V2, temperature T2, and number of molecules N2. Now remember from the problem statement, and also identified over here on the board, that V1 and T1 don't change, so that V1 and V2 are the same, and T1 and T2 are the same. So now the ideal gas law is written right here. It is going to be used to guide us. We know that the new number of molecules N2 that are in the tire is equal to the old number of molecules N1 minus the number of molecules that were released. So notice that if we apply the ideal gas law to this new situation, we know the new volume is the same as the old volume. We know the new temperature is the same as the old temperature. So in order to solve for the new pressure, P2, the only unknown here is the new number of molecules. So if we can find this new number of molecules N2, then we can immediately solve for the new pressure P2. So let's use this formula to find N2, and then we can come back, use the ideal gas law applied to the second situation here, and we'll solve for the new pressure. So what is N1? Well, we're going to use Pivnicht, the ideal gas law, applied to the first situation. So P1V1 is equal to N1K T1. Notice the only unknown here is N1. So rearranging, N1 is equal to P1V1 over KT1. So those values all here on the left-hand side of the board, I plug in P1, 7.00 times 10 to the fifth newtons per meter squared, multiply that by the volume, 2.00 times 10 to the minus 3 cubic meters, and then divide by Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per Kelvin, and then divide that also by 2.91 times 0.15 kelvins. So when I put all these numbers in, what I get is a number of molecules originally in the tire, 3.484 times 10 to the 23rd molecules. So that's how many molecules occupy my tire originally. So now I can find N2 if I can find the number of molecules released. I now have the original number of molecules N1. So here it is. So again, using PIVNICT, the ideal gas law, I can apply it to the number of molecules released. So the pressure at which the molecules were released times the volume of molecules released is equal to the number of molecules released times Boltzmann's constant times the temperature they were released at. And that's, of course, the temperature T1 or T2. They're the same. So rearranging again, solving for the number of molecules released, it's going to be P prime V prime over KT1. So P prime, the pressure at which they were released, atmospheric pressure, 1.013 times 10 to the 5th newtons per meter squared, times the volume that was released in standard units, that's 1.0 times 10 to the minus 4 cubic meters, divided by Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin, and then again divided by 1.91.15 Kelvin. When I plug all those numbers into my calculator, I get 2.521 times 10 to the 21 molecules. So as the 100 cubic centimeters of gas was released, 2.521 times 10 to the 21 molecules left the tire. So now we have the ability to immediately calculate N2 as we now have N1 and N prime. So N2, the new number of molecules remaining in the tire, is the old number of molecules N1 minus how many were released. And so when we take 3.484 times 10 to the 23rd molecules and subtract the 2.521 times 10 to the 21 molecules, what we end up with is 3.459 times 10 to the 23rd molecules remaining in the tire. Now we have N2. So again, coming back to the ideal gas law and writing it now in terms for the gas contained in the second situation, rearranging for P2 in this case, we have everything but P2 at this point. So it's N2K T2 over V2, plugging in the 3.459 times 10 to the 23rd molecules times Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per Kelvin, times the temperature, 291.15 Kelvin, and dividing by the volume V2, 2.00 times 10 to the minus 3 cubic meters, we get a new pressure for this tire with the number of molecules decreased as 6.95 times 10 to the 5th newtons per meter squared. And we see we expected the pressure to be lower because we aren't changing the volume or the temperature, but we're removing some of the molecules. And so we do expect the pressure to drop. And we do see it drops from 7.00 times 10 to the 5th to this new pressure, 6.95 times 10 to the 5th newtons per meter squared. So this gives us an idea of how to apply some of these concepts from chapter 13 to a real problem, one that we find in the back of the textbook. So we'll see you next time. Thank you.